This lecture will give a brief introduction to set function. So far we have learned set, set operations, field, sigma field. So with this knowledge, now we will define a set function. To define a set function, what we need, first we have to define a measurable space. Then after getting the measurable space, we will define set function and we will describe few of its properties. So once we know the set function, then we will try to give few examples of set function. Then we will describe two of the important properties which we know as additivity and sigma additivity. We will find the interrelationship between sigma additivity and additivity. That means if a set function is sigma additive, then whether it is additive or not, and the converse. We will go through all these concepts with the help of examples. So this lecture is aimed to get an idea about the set function and its operations. With the knowledge of set, field and sigma field, now we will be defining set function. So let us start with the definition of set function. Consider the reference set omega and a class script A. This class consists of all possible subsets of real line R. These two quantities omega and script A together is called measurable space. So measurable space consists of two quantities, the reference set and the class we are talking about. Now a set function is defined on this measurable space. By definition, a set function gamma on this measurable space omega and script A is an extended real valued function defined on this script A. Now what do we mean by extended real valued function? Now we all know that real line, by real line we means it is minus infinity to plus infinity. By extended real valued function we mean that this gamma can take the value minus infinity as well as plus infinity. So that means this gamma, this set function is a mapping which maps this class script A into extended real line which is consisting of minus infinity as well as plus infinity. So we denote it as a closed set where both the extremes are included in the set. Let us talk about few examples. Suppose the reference set consists of natural numbers 1, 2, 3, 4 like this, and script A consists of all subsets of this omega. So this is a class set of sets where the sets will be constructed from this subsets of omega. Now if we define the set function gamma A as the number of elements in A, how many elements are there in a set A? That is my set function. So for different sets A, I will have different numbers. For example, let us consider the set A consists of these elements 1, 3, 5, 8 and 9. Since gamma, the set function, is defined as number of elements in the set A, so clearly gamma A will be 5 because in this set I have only 5 elements. So this is a finite number and real number too. Now if we have a set which consists of infinite number of elements, for example if I consider all odd numbers of this real number, so my set consists of all odd numbers. Now if I ask the same question that how many elements are there in A, now if I ask the same question that how many elements are there in the set A, the answer will be infinity. So this shows that the set function can be finite as well as can be infinite. That is why the set function is defined in an extended real valued function. So that means it can be infinity in either cases. Now if I consider the second example, suppose the reference set omega is the real line, and in class we are considering all intervals of the type A open, B closed. So, this sort of intervals we are considering, one left side is open whereas right side is closed, and with this normal assumption that A is less than B and both are not only finite, it can take both the values can take minus infinity as well as plus infinity. Now, we define the set function gamma a b as b minus a, as if we are considering the length. So, if I consider the interval 1 and 3, that means gamma 1 3 is b minus a, 3 minus 1, that is 2. Now, if one of the element is minus infinity or it is plus infinity, then this will be just infinity. So, here also the set function can be infinity. Now, we will define what do we mean by additive and sigma additive set function. First, we will start with additive set function. When a set function is said to be additive set function. Now, we say gamma as an additive set function. Gamma is defined on the measurable space omega and script A. Omega is the reference set and script A is the class. Then for a finite number of sets A1, A2, A3, An, if gamma union over I from 1 to n Ai is equals to sum over I from 1 to n gamma Ai, that means whenever the Ai, the sets, they are disjoint, that means Ai intersection Aj is phi for all I not equals to j, whenever we have disjoint sets, and if all the sets belongs to the class script A, then gamma of union will be sum of gamma. That means that the set function of union of sets will be summation of individual set functions. So, we can assume in this way that if you have a larger set and if you want to find the set function of a large set, we can break it into piecewise and we can add them with the consideration that each piece will be disjoint, they are mutually disjoint. Now, this function is called, this set function is called additive set function. Now, if we extend the concept of this additive set function from finite number to countable number, then it will be called sigma additive set function. So, by definition, a set function gamma defined on the same measurable space omega and script A is the class which consists of all the subsets of omega. We call it sigma additive if gamma I from 1 to infinity Ai is sum over I from 1 to infinity gamma Ai, where all the Ai's belong to the class script A and Ai intersection Aj phi whenever I is not equals to j. That means, we are considering all disjoint sets. So, the concept of additive and sigma additive is just an extension from the additive to sigma additive, where n is finite we are considering additive set function, when n is infinite we are considering sigma additive set function. So, quite obvious that sigma additive set function is definitely additive, but converse may not be true. We will show this in later examples, where we can have some set functions which are additive, but not sigma additive. Now, one interesting question is that for a phi, for null set phi, what should be the set function? So, we will be assuming gamma phi to be 0. How? Well, the proof is more or less trivial. Only restriction that we want to have is that the set function of a set A, gamma A, must be finite. If gamma is finite, then we can write gamma A as gamma A union phi union phi union. So, we have countable numbers of union over phi. Now, if we take union of phi to any set, the set will remain all the same. Moreover, this A and phi, they are mutually disjoint. If they are disjoint, then I can break this union into sum. So, I have gamma A plus gamma phi plus gamma phi plus gamma phi. So, I have countable number of gamma phi. Now, here comes the restriction that if gamma A is finite, then this gamma A will be cancelled out from both the sides and it will yield the result that gamma phi is equals to 0. So, under the restriction, under the condition that set function is finite, only then we can say that for that set function, the set function of a null set will be 0. Let us consider another example. Now, we define a set function mu. This is defined over the power set of real numbers. So, all possible sets which are made from the set of real numbers, and we define mu A if the element 0 belongs to the set A, and mu A will be 0 if 0 is not in the set A. So, thus we are defining a set function in this way, depending on the situation whether the element 0 is within the set or not. Now, if we consider A1, A2, A3, An as a sequence of disjoint sets of real numbers, then it is possible that either none of the sets contain 0 or precisely one of them does. Now, consider the first situation when none of the sets contain this element 0. If they do not contain 0, then by definition of the set function, if I take the union over I from 1 to infinity a I, the set function will remain 0, and the summation if I take I from 1 to infinity mu a I, that will also be 0, because in each case mu the set function value will be 0. Now, on the contrary, if precisely one of them contains 0, then what will happen? Then to the left side, if I consider mu union over I from 1 to infinity a I, in all these a I's 0 is contained. So, mu must be 1, and it is contained in only one sets. So, to the right hand side, if I add all the mu's for I from 1 to infinity, sum over mu a I will also be 1, because 0 is contained in only one of these a I's, and suppose it is in A5, then mu A5 will be 1, rest will be zeros. So, whatever may be the case, that whether none of the sets contain 0 or one of them contains 0, in each case it holds. So, this is an example which shows that how a set function can be constructed on the basis of the real numbers, which is additive as well as sigma additive. Now, there is a question that if a set function is sigma additive, can it be additive also? Well, the answer is trivial, true, because whenever we are considering sigma additivity, we are saying that we are taking countable unions. So, if any result is true for countable number of unions, it will be true for finite number of unions too. Now, whether the converse is true or not, this is the basic question, that if a set function is additive, whether it can be sigma additive or not. We will give one counter example to show that even if it is additive, it may not sigma additive. Now, for this we are considering one example. Suppose the reference set is an interval which is 0 open, 1 closed. So, this is the reference set we are taking, and we are constructing a class of intervals which is of the same form, left side open, right side closed. So, it is A, B, this is the interval we are considering. So, we are considering all possible of intervals and we are making it a class. Now, we define the set function gamma A B as B minus A if A not equals to 0, and if A equals to 0, this set function will result in value 0. So, this gamma can take two values, B minus A or 0, depending on the value of A. If A is non-zero, it will be B minus A, if A is 0, it will be 0. Now, we have to show that this is additive, but not sigma additive. Now, we are considering a set A n depending on the suffix n, it is of the form A open, B closed. So, we are taking 1 over n plus 1 and 1 over n. Now, by definition of the set function, if we want to find the value of the set function gamma a n, by definition it will be 1 minus 1 by n minus 1 by n plus 1. Why? Because the left element is not 0. So, the gamma function is defined in such a way that if a is not equals to 0, gamma n will be the difference. So, that is why the gamma n will be 1 over n, that is the b here, minus 1 over n plus 1, this is a. And now, if I take the union over I from 1 to infinity a n, what I will get? Now, if I take the union of all these a n's, then what I will be getting is the reference set, 0 open, 1 closed. Now, if I take the set function over this unions, what I will be getting? Now, since the left element of that interval is 0, by definition of the gamma function, the set function, it is infinity. So, gamma union over n from 1 to infinity a n will be infinity. Now, look at the sum. So, it is to be noted that a1, a2, a3, these are all disjoint sets or disjoint intervals. Now, if I add all these gamma functions, what I will be getting? Now, if I add them together, it will be a sum over 1 over n minus 1 over n plus 1, where n ranges from 1 to infinity. So, this sum is very special in mathematics. So, this sum is something like that, 1 minus half plus half minus 1 by third plus 1/3 minus 1/4 and so on. So, a close look at the sum will reveal that it is nothing but 1. So, what we will be getting, that gamma union over n from 1 to infinity n is infinity, whereas sum over n from 1 to infinity gamma n is 1. So, this shows that though this set function is additive, it is not sigma additive. So, additivity does not mean all the time that it will be sigma additive too, but the converse is always true. That means, if the set function is sigma additive, it will be additive, but if it is additive, sometimes it may not be sigma additive. In this lecture, we have learned set function, their properties, and we gave few examples. Now, this set function will be laying down the foundation for the next course, that is measure. We will define measure as a special class of set functions satisfying few of the conditions. So, that will be discussed in later lecture.